All right, hello everybody. Welcome to the first annual Scalar Capital Summit. My name is Jordan Clifford. I'm the co-founder of Scalar Capital along with Linda. So Linda's going to introduce you to our first speaker of today. There you go.
Hi everyone, hi, I'm Linda. So originally we were going to have opening remarks and talking about Scalar, but I attended an event called Crypto Springs that Meltem and Elizabeth Stark had put on a couple weeks ago, and Tess gave a talk on distributed consensus, and I thought it was so amazing that this is really just the best way to open up the summit. So without further ado, please give a warm welcome to Tess.
Cool. Yeah, so I met Linda a couple weeks ago, and she asked me to give this talk, which I gave a few weeks ago. And it really is just my attempt at cutting through some of the blockchain hype. Because I really think the best way to do that is to just take some of these principles and ideas that underpin blockchains and look at them kind of from first principles. And I think distributed consensus is a really good candidate for that, because the word consensus gets thrown around all the time, almost as a buzzword in the space. But this is a problem that computer scientists have been working on for a really long time. So, why not? It's never too early for some computer science, right? And I just want to help people understand sort of how we're not alone in the space, and also what the problems are, especially so that when you come across a new protocol, maybe one that has a novel approach to consensus, you'll have a more intuitive understanding of that, and maybe also of some of the trade-offs that that protocol might be making. Okay, so to begin, let's imagine that we have this system with 5 nodes. And all of these nodes can talk to each other, and each node has a slot for the value. And we want all these nodes to choose a value for their slot. And that value should be the same across all the nodes. And that might sound like a little bit contrived, but really that's just the same problem as getting every node to agree on what the next block is, right? Or if a transaction happened. Okay, so how might we do this? Well, naively, we could just have one node propose a value x to every other node in the system. And then once all of these other nodes say, okay, yep, good, our proposer node can then adopt x as its value, and the other nodes can adopt it as well. And this will work, but there's a couple of problems here too. So, for example, what if this other node wants to suggest a value at the same time? Or what if there's a network partition where some of the nodes can't reach one another anymore? Or what if there's just a lot of nodes, right? Then it would take a really long time for any proposer node to reach out and hear back from every other node in the system every single time there's a change. Or what if one of the nodes goes offline? Our proposer node would then wait forever, waiting for that other node to come back online and give them that receipt, right? And finally, there's a lot of other problems that computer scientists get really excited about, but I won't go into them at 9 in the morning. Okay, so broadly speaking, consensus algorithms are the solution to this problem. And one of the oldest consensus algorithms is called Paxos. Now, if you've heard of Paxos, you may have also heard of the problem with Paxos, which is that no one actually understands it, people say. And in fact, in a paper introducing another consensus algorithm, which is called Raft, the authors explain that they went to an academic conference and they surveyed people, and they found very few people who were actually able to answer questions about Paxos's nuances. In fact, they say they themselves didn't understand it until they spent a year designing an alternative protocol. So that probably sounds really daunting, but I want to make something clear, which is that the trouble with Paxos comes from the fact that a lot of its behavior is unspecified. So in the original Paxos paper, a lot of details are left sort of as an exercise to the reader. And that means it's really difficult to implement correctly. So to accommodate that, there are dozens of variations, many of which are very complex themselves. But basic Paxos is actually pretty intuitive. So it addresses all of those problems, all of those little failure scenarios that I just showed you, by building on top of that first naive solution. So the first naive solution relied on a single node proposing a new value to all the other nodes in the system, and Paxos works in roughly the same way too. So in Paxos, consensus rounds are organized by ballots, and the proposing node sends out a ballot that the other nodes will have to vote on. So let's begin by looking more closely at a node. In Paxos, our node no longer has a single slot for a single value. Now it has 3 slots. And one is for the value, as before, but now there are 2 new values. And these are both numbers: the number of the ballot that this node has most recently prepared, and the number of the ballot that this node has most recently accepted. So to explain what that means, let's go back to this 5-node system. So in this example, all of these nodes can be both proposers and acceptors. They can both propose new values and vote on whether or not to accept them. And in a more complex system, you can imagine that there might also be like observer nodes who just talk to all of these acceptors and learn what the new value would be. Okay, so now let's say that this node, again, would like to update the value, so it sends off a message to all the other nodes in the system. Prepare the ballot n prime, where n prime is the ballot number that follows ballot n. So you can notice that the proposing node also sends this message to itself, because it can also vote on this ballot. And if it's helpful, you can think of this prepare message as a warning to the system that a change is coming. When the nodes receive this prepare statement, they check it against the largest ballot number that they've previously prepared. So in this case, they can see that n prime is greater than n, so they ACK, or acknowledge, the ballot. So in other words, they're now telling the proposer that they've never prepared a later ballot, so the proposer is okay to proceed with this one. So at this point, the proposing node needs to count the number of ACKs it's received. So if it's received ACKs from a majority of nodes, it can proceed with the ballot. And now it sends another message to all of the nodes. And that message is accept the ballot n prime. So you should think of this message as a command. It's telling the other nodes that they should accept this ballot. And this message doesn't have just the ballot number, it also has the value that the nodes are supposed to adopt. So in this case, that's x. Once a node receives this accept command, it updates its value to be x, unless it's already received a new ballot with a ballot number higher than n prime, in which case it waits for the rest of the newest ballot. Okay, so that may all seem a bit needlessly complicated, but now that we're armed with this multi-stage consensus process, let's see how some of these failure scenarios play out. So first, let's look at what happens if a node goes offline. So let's say that this proposing node sends out its prepare statement, but this other node goes offline before it can respond. So all of the other nodes can still send their ACKs back to the proposer. So the proposer, when it counts its ACKs, it will see it still has received responses from a majority of the nodes. So it can proceed and finish the round. Now, as a slightly more complex example, let's look at what happens if 2 nodes propose values at the same time. So let's imagine that both these nodes send messages to prepare the ballot. And the first proposer's messages are represented by these solid lines, and the second ones are represented by these dotted lines. And due to like network latency or something, these dotted messages get there a little bit after the first ones. So at this point, every node will only send an ACK in response to the first prepare statement it received. So they'll send an ACK back to the first proposer, but not to the second. So only the first proposer will actually receive those ACKs from a majority of acceptors, and only it can continue with the ballot process. The second one has to stop because it didn't receive enough ACKs. So now the first one can send out that accept command with a new value, and all of the nodes will adopt it. Okay, so that's great. We maintain consistency across all the nodes. But the devil's in the details, and while I've presented what I think is a pretty good high-level overview, there are lots of corner cases in these examples, as well as entirely different failure scenarios, like network partitions and things like that. So this is a good time to take a step back and look at this little universe of consensus algorithms. So this is what we have so far. We have this problem, the consensus problem, and here are 2 solutions that I've mentioned, Paxos and Raft. And there are other algorithms too, but these are the 2 that I've mentioned so far. But you might have also noticed that all of these examples rely on every participant following the rules. So the proposers never send out accept statements for ballots they haven't prepared, nothing like that. And that kind of failure, where nodes stop following the rules and start behaving maliciously, is called a Byzantine failure. So Byzantine failure is named after the Byzantine Generals problem, which is a classic computer science problem formulated as a parable. And as an aside, academic computer scientists really like doing this kind of thing. They really like making fake historical narratives to illustrate challenges in computing. So, for example, Paxos is named after a Greek island because its author invented an ancient Greek democracy that uses the Paxos algorithm to vote. And he also tried to teach this algorithm to his students by dressing up like Indiana Jones and pretending that he'd discovered this ancient society during an archaeological dig. But he also said later that although everyone remembered Indiana Jones, no one remembered the algorithm. So clearly he needed some use case like Bitcoin to make it more exciting. Anyway, in the Byzantine Generals problem, there are some generals who've surrounded a city and they want to decide if they're going to attack or hold back. And some want to attack and some want to hold back, but the important thing is that they all decide what to do together. Because if only a few of them attack, then those generals will be doomed, and that would be much worse than a coordinated retreat. So the thing that makes this tricky is that there could be malicious generals who can selectively tell different things to different generals. So, for example, if the generals are split down the middle, the malicious general might tell the generals who want to attack that they should, and the same general could tell everyone else to stay back. Then just under half the generals would attack, and that would be a big failure. Again, that maybe sounds contrived, so as a simple technical example, imagine that a proposer node asks the other nodes to prepare a ballot with a number far in the future. It would then freeze them until that ballot rolled around, possibly for years. Okay, so how can we address this kind of failure? Well, just as we built Paxos up from our first naive solution, we can also build up another algorithm that looks an awful lot like Paxos, actually, but with a more descriptive name. And that's practical Byzantine fault tolerance, or PBFT. And like Paxos, PBFT requires nodes to go through a multi-step voting process, but it becomes even more complex. It introduces more rounds of voting and even more types of nodes. So this diagram shows all of the messages that need to be sent in order to tolerate a single Byzantine fault during a single vote. It gets pretty gross, actually. And in fact, it's complex enough that this paper, which puts practical in scare quotes, was published 12 years later, just warning people that PBFT was maybe too tricky to even use in production. Nonetheless, at this point, it's safe to add PBFT to our diagram. So PBFT both solves the consensus problem and can handle Byzantine faults, so we can put it in this new Byzantine safe box. PBFT keeps working as long as fewer than 1/3 of the nodes are misbehaving. And this sounds pretty good until you realize that now we have another problem. What stops an attacker from just spinning up a bunch of new nodes that can behave in malicious ways? So that's called a Sybil attack, and classically, PBFT prevents it by just forcing nodes to negotiate their membership up front. So in other words, new nodes can't join. And that doesn't really work for a public blockchain network, right? So now we need another box for our universe, this Sybil safe box. What can we put in this box? Well, at this point, you know, this is like a cryptocurrency crowd, so probably everyone is saying, hang on, what about proof of work? Doesn't it solve all of these problems? Well, in short, yes. So in proof of work consensus, every validator node composes a new candidate block from pending transactions, and then the node then attempts to guess a nonce that when combined with the block contents can be hashed to produce a value that's smaller than some threshold, right? So you're probably all sort of familiar with this process. So in this illustrated example, you can see all of our nodes have made some guesses, and after some time, this node finds a nonce that produces a suitably small hash. So at this point, it can broadcast the nonce and the hash and the block to the other nodes in the system, and then the whole system can advance to the next block. So the idea here is that the node that gets to identify the next block will be randomly chosen, or at least chosen in proportion to the amount of hashing power that each node has. And there's some historical safety here too, because it costs so much energy and takes so much time to find a valid hash to propose a new block that it would be infeasible to try to rewrite any old blocks. And yes, in this system, it's possible that multiple nodes can propose different blocks at the same time, but in Bitcoin, that's also okay. Because at any given time, the longest chain will be the valid one, so proposing nodes are incentivized to choose the longer branch. And eventually, all the nodes will end up on the right branch. So proof of work sacrifices a little bit of consistency for simplicity and availability. And as in other systems, not every node in the system has to act as a proposer, but one neat thing about proof of work is that other nodes can easily check the proposer node's work by just hashing each block and checking it against its hash. So now it's safe to put proof of work in our Sybil safe box. But proof of work has some problems. So first, there are tricks, like ASICs, that nodes can use that increase their hash power, and then by extension, increase the likelihood that they get to propose the next block. And not every proof of work blockchain is vulnerable to this because it does depend on that hash function that's being used. But this does make consensus rounds less fair. And more importantly, it's infamously expensive to run, right? So all of those articles about how Bitcoin is ruining the environment are based on the energy that's needed to calculate and recalculate all of those hashes. So at this point, we might look again at our little universe and create a new target. Is it possible to have a consensus algorithm that is both Sybil safe and doesn't boil the ocean? And it turns out, yes. One of the most popularly mentioned options is proof of stake, which is the consensus flavor that Ethereum is moving to in its final stage. And I say flavor because proof of stake isn't a single algorithm, but rather a family of algorithms. So some proof of stake algorithms are like proof of work in that they determine the next proposer node in a probabilistic way. But in proof of work, nodes can increase their odds by increasing their hash power, and in proof of stake, nodes increase their odds by increasing their stake. So depending on the implementation, this stake can either be the amount that the node holds, or it can be the amount that has been put into kind of like a security deposit. And in that case, if the proposer node misbehaves, it can effectively be fined through that security deposit. But that leads us to another question. How can we know if a proposer node has misbehaved? Maybe we need a way to let the other nodes vote on whether a proposer node is suggesting valid values. And that word, vote, should be bringing you right back to Paxos and PBFT. And in fact, there are consensus algorithms that combine the strengths of both proof of stake and PBFT. And a very popular one is Tendermint, which lets nodes vote on proposed blocks using a technique that looks a lot like PBFT. And as you might remember, the big problem with PBFT is that it's vulnerable to Sybil attacks, where an attacker creates lots of malicious nodes that sort of overwhelm a consensus round, right? Well, Tendermint protects against those attacks by using proof of stake. So a node must first put up some collateral before it can become a proposer node, which increases the cost of entry. And then if it behaves maliciously, that collateral is slashed as punishment. So in other words, it just becomes very, very expensive to attack the network. But there's one last issue that all proof-of-stake systems have, and that's that they tie consensus power directly to resources. So those who hold the most resources, the most capital, have the most control over network consensus. And that might be fine for a lot of applications, but what can you do if you want to decouple these things? So let's add another box to our universe to capture this important property. Proof-of-stake systems are, shall we say, a little bit kleptocratic, and proof-of-work systems are not. So this is where yet another family of consensus algorithms comes in handy. And that's federated consensus, which leverages pre-existing systems of trust. So we can add to our universe a concept of trust, which neither proof-of-stake nor proof-of-work require. My favorite federated consensus algorithm is SCP, which is the Stellar Consensus Protocol. And this is where I need to insert a little disclaimer, because I do work for a company that builds on the Stellar network. But SCP is genuinely really cool, and it's cool because it uses a voting system that's similar to Paxos or PBFT, but instead of using proof of stake to determine membership in the set of validating nodes, it lets every node choose which other nodes to trust. So this strategy works especially well for Stellar, which is at its best as a medium of exchange for third-party tokens. And on the Stellar network, these third-party tokens are created by trusted issuers. So if you're already trusting issuers to remain solvent and redeem your tokens, why not trust them to manage your consensus too? So more concretely, you can imagine that you decide to agree on a transaction when your counterparties and issuers do. So you would then transitively build a network of trusted nodes. And that might sound a little bit far-fetched, but the literal internet is proof that these transitively trusted networks can emerge. Since ISPs are decentralized decision makers, they could have diverged and created many separate internets. But because everyone wanted to talk to everyone else, they didn't. So as an example of how this works, look at this network, where some of these nodes trust A as an issuer and some of them trust B. But B also trusts A because it wants to work with A's token. So when A declares that a transaction has happened, these three nodes adopt it. And then when this last node sees that B has adopted it, it adopts it as well. So we can see that SCP fits here in our consensus algorithm universe. It does require proof of work, it does require more trust than a proof of work algorithm, but it's also much cheaper to run. It admits that not all consensus problems can be solved with computers alone. And even proof-of-stake systems admit that a bit, because when a new node joins a proof-of-stake system, it has to ask another node for the system's current state, and it has to trust that. So there's this theorem from academic computer science, and it's called the CAP theorem. It's about 20 years old, and the CAP theorem says that any distributed system cannot have consistency, availability, and partition tolerance. At most, a system can have 2 out of 3. And after learning about Paxos, maybe you can see how that would start to emerge. And maybe you can start to see another necessary trade-off emerge for blockchains, the trade-off between efficiency, fairness, and minimized trust. Proof of work minimizes trust and prioritizes fairness, but at the cost of efficiency. Proof of stake prioritizes efficiency and minimizes trust, but it's not fair to those who have fewer resources. And finally, federated consensus, like SCP, prioritizes fairness and efficiency, but it requires nodes to choose other nodes to trust. So I hope that I've given you a healthy appreciation of all of those trade-offs, and if you have questions, let's talk at lunch or at a break.